Chapter 7, Estimates and Sample Sizes. Alright, as you can see, we got just a real small intro, review, and preview, and then 3 sections to this chapter. Review. So, in chapters 2 and 3, I know that was a while back, we used descriptive statistics when we summarize data using tools such as graphs and statistics such as mean and standard deviation. In chapter 6, that's when we started going over z-scores, critical numbers, critical values, so somehow all of this has to come together. Why do we use critical values? We never really used them that much, but I showed you how to find them on the table, your z-score chart. It says z sub alpha denotes the z-score with an area of alpha to its right. So remember the way that the z-score charts work. If we have z sub, like this right here says 0.025, then that means the area to the right we want to be 0.025. So if you recall the way that our table gives us values, if we want the area to the right to be 0.025, something really, really small, our chart gives us, if we look up an area, will give us cumulative area from left to right. So the actual area that we would want to look up in our chart to find that critical value would be 1 minus 0.025. So we want to look for the area 0.975 in our chart and see which z-score that gives us. Then that would be our critical z-value. Okay. Of course, that's just a little review. Surely you knew that anyway. Alright, and this slide shows that you would find that's 1.96. Just a little extra to go with that. If you wanted to know the critical z-score whose area to the left was 0.025, it would be negative 1.96. Because the z-score chart and the bell curve and all that area underneath, that's all symmetric. All right. Okay, so in this chapter, what are we going to do? This is the beginning of inferential statistics. The type of statistics that's usually used in studies and journals so that you can learn how big a sample size needs to be. If your sample size is large enough, looking at margin of error, looking at intervals, confidence intervals, and things like that. So 2 major activities of inferential statistics are to use the sample data to estimate values of the population parameters and to test hypotheses or claims made about population parameters. We introduce methods for estimating values of these important population parameters, proportions, means, and standard deviations or variances. So really, once we learn how to use a value like a proportion to estimate values or to find intervals, confidence intervals, find margins of error and all that, once you learn how, it's the same thing for these other types of parameters, the means, the standard deviations or variances. It's just different formulas, but you're doing the same stuff. Okay? So if you get really good with one of these parameters, then the other one should pretty much fall in place. We also present methods for determining sample sizes necessary to estimate those parameters. So, how big does your sample size need to be so that you can confidently state something like statistics is easy for 90% of all students. You know, how big of a sample would you need to have? Well, it wouldn't exactly be something like that, but statistics definitely is not easy. But it's not too bad. All right. So let's start section 7.2. Estimating a population proportion. All right, so we're going to go over how to estimate the value of a population proportion. The sample proportion is the best point estimate of the population proportion. So a sample proportion is what we will use. It is the best point estimate of the population proportion. We can use the sample proportion to construct a confidence interval. All right, how confident? We can construct confidence intervals where we're 95% confident that some value actually lies in a range. We can construct confidence intervals so that we're 95%, 99%. We have various different confidence intervals that we can figure out. And then we're going to learn really how to interpret those confidence intervals. And lastly, we are going to go over how to find the sample size necessary to estimate a population proportion. What is a proportion? You know, just think back. Proportion. Probably going to be some type of fraction that you could have as a proportion. You know, and from any fraction we can get a decimal. So some type of population proportion is what we'll be looking at. Now the point estimate, which we said is the best way to describe the population proportion from the sample proportion. A point estimate is a single value or point used to approximate a population parameter. Point estimate is a single value or point used to approximate a population parameter. All right, we use the sample proportion p hat. All right, it's a p with a little up caret. That is the best point estimate of the population proportion p. P hat, the sample proportion, is the best estimate of the population proportion p. So we get some value from our sample size, from our sample of whatever, and that's p hat. That is the best point estimate of the population proportion p. All right, so here's an example of finding a sample proportion or point estimate. The Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. The best point estimate of P, this is the population proportion, P, is the sample proportion, this 85%. 85 out of every 100, or 0.85, is the best point estimate of the population proportion, P. All right. And this comes from the sample that they took in their study. All right, from that, there is a way to find something called a confidence interval, or an interval estimate. I will always call it a confidence interval. Think about any type of interval. What does the word interval mean? Usually when I think of intervals, I start thinking of things like range and domain, things that we learn in college algebra. And it is going to be somewhat similar to that, we're going to have some type of interval where we have maybe like a largest number and a smallest number that will contain some type of parameter, which right now we're talking about proportions. Okay, so we'll set it up and you'll see that it's not much different from any other interval. It's just that you have some type of statistic in that interval, or you want to be so much confident that the statistic actually relies in that interval. Okay? So a confidence interval is a range or an interval of values used to estimate the true value of a population parameter. A confidence interval is a range of values used to estimate the true value of a population parameter. The abbreviation for confidence interval, capital C, capital I. So the CI, confidence interval. All right, a confidence level is the probability 1 minus alpha. All right, confidence levels could be the most common levels are 90%, 95%, or 99%. Now, the way that you get the alpha for each one of these, 90% can be written as 0.9, right? So 1 minus 0.9 is 0.10. So this alpha here, 0.10, is for 90%. 95%, you can write that as 0.95. So the way you would get its alpha is 1 minus 0.95, or 0.05. So alpha is 0.05. That's for a 95% confidence interval. Okay. 99% confidence interval is 1 minus 0.99. So that's 0.01. So a confidence interval or confidence level 99% matches up with an alpha of 0.01. So these are our three most common choices. You can choose other things, but these are used a lot. Now, let's go back to this definition. I want to read through it. A confidence level is the probability 1 minus alpha expressed as the equivalent, or often expressed as the equivalent percentage value, that the confidence interval actually does contain the population parameter. Let me repeat that. So I'm going to skip some of this stuff and tell you the meat of it. A confidence level is the probability 1 minus alpha that the confidence interval actually does contain the population parameter. So you could be 99% confident that the interval actually does contain the proportion that you have, or the standard deviation that you have, or the mean that you have. All right. And of course, that is assuming that the estimation process is repeated a large number of times. You'll see me use confidence interval, confidence level. Confidence level is that actual percentage, or alpha equals 0.1, 0.05, or 0.01. That's the confidence level. The confidence interval is an actual interval. Like you would have, say, in algebra, where you have an interval. There's a couple ways to write that interval. Maybe I'm just going to write just an algebra interval. This is the interval from 0 to 10. It's not going to look exactly like this, but there will be a way to write it like this if you want to. Alright, so here's an example of a confidence interval. Alright, so this is a proportion P. We don't know, we don't have the problem, but I would assume that it's probably something related to the chapter problem, maybe or maybe not. But here's the proportion P, and here's the interval that's been created. This is a confidence interval. Alright, now it doesn't mean that P is between these two. What does it actually mean? We are not, and this is for a confidence level of 95%. We are 95% confident that the interval from 0.828 to 0.872 actually does contain the true value of the population proportion P. This means that if we were to select many samples of size 1007 and construct the corresponding confidence intervals for 95%, 95% of them would actually contain the value of the population proportion P. So we would have to do, studies over and over and over with 1007, and we would be 95% confident that the interval we get contains the true value of the population proportion P. Caution. This means make sure that you know the correct interpretation of the confidence interval. Confidence intervals can be used informally to compare different data sets, but the overlapping of confidence intervals should not be used for making formal and final conclusions about the quality of proportions. All right. Using confidence intervals for hypothesis tests. A confidence interval can be used to test some claim made about a population proportion P. For now, we do not yet use a formal method of hypothesis testing. That's chapter 8. So we simply generate a confidence interval and make an informal judgment based on a result. All right, we're going to need to be able to find critical values. A standard z-score can be used to distinguish between sample statistics that are likely to occur and those that are unlikely to occur. Such a z-score is called a critical value. Critical values are based on the following observations. Under certain conditions, the sampling distribution of sample proportions can be approximated by a normal distribution. A z-score associated with a sample proportion has a probability of alpha divided by 2 of falling in the right tail. So let's take a look at what we would actually be looking at if we were discussing critical values. So critical regions or critical values, the actual critical value is here, and then the area to the right or the area to the left, that's the actual critical region. Okay? Now it's called critical, this Z is called a critical value because it separates values that are likely to occur, all this in here, and unlikely to occur, the stuff that would be in here or in here. Alright, so the actual z-score itself is just the number here that is like a boundary. So if we find a data item is in here, then it's unlikely that data item is unlikely to occur. But if we find a data item that's in here, then that means it's likely to occur. And this slide goes on to just reiterate. A critical value is the number on the borderline separating sample statistics that are likely to occur from those that are unlikely to occur. The number z sub alpha over 2 is a critical value that is a z-score with the property that it separates an area of alpha over 2 in the right tail of a standard normal distribution. Alright, so let's look at how would we find, and this is something we've already done, but how would we find the critical value z sub alpha over 2 for a 95% confidence level? Alright, this is the same thing pretty much that we went over in the little review back in 7.1. So if we have a 95% confidence level, that means that alpha is equal to what? 0.05. So 95% confidence level, alpha is 0.05. Alright, so to find the critical z value, critical z is alpha divided by 2. So the critical z value is going to be 0.05 z sub 0.05 divided by 2. Alright, and 0.05 divided by 2 is 0.025. Okay, and so where I drew the picture up here, if I wanted to know what this z-score was, this critical z, then I want an area to the right of 0.025. That also tells me that the area here, over here somewhere, there's going to be another critical z value with an area of 0.025 because the bell curve, all this is symmetric. So if I find the one that's negative, then to find the one over here, you just make the z-score positive. Or if you find the one that's positive, if you wanted to know the one over here on the left, you just make the z-score negative. So do whatever you have to do to find the actual z-score. You just want to see which one is closest to 0.975, which z-score is. And that would be this positive critical z number. If you needed the other, you can just make it negative. Okay, and that's what's shown in this graph here. The critical z-score for a 95% confidence level is always 1.96. And so that's the positive critical z-score. That's the z that borderlines the things that are likely to occur from unlikely to occur. Same over here on the left side, things that are likely to occur and things that are unlikely to occur. Okay. All right. So I told you earlier that the most 3 common confidence levels were 90%, 95%, and 99%. If you were to look at your z-score chart, so how do I find that again? You can go to your book, the back appendix here. Scroll down until I get to, here's my z-scores. If you look at the bottom of your positive z-score chart, look at these common critical values, confidence level. This is 90%, 95%, 99%. 1.645 for 90%, 1.96 for 95%, and 2.575 for 99%. If this class was longer, you would use those values so much that you never forget them, really. But, you know, we'll just use them in this chapter and the next chapter. Now, we could find a critical value for 98% if we wanted, or for 99.9% if we wanted. The way we do that is we figure out what alpha is, we divide it by 2, and then we use that area with our z-score chart to figure out the z, the critical z. Alright, so here's those values again. Alright, so now we're going to look at estimating the margin of error. We denote the margin of error by capital E. Alright. It said it is the maximum likely difference between the observed proportion p hat and the true value of the proportion p. So for the margin of error for a proportion, since it's different for every parameter of statistic we look at, but for a proportion we can find the margin of error. I say that equals the critical z-score, that's z sub alpha over 2, times the square root of p hat times q hat divided by n. If you look at the formula sheet that comes with your book, it should be there. Alright. So this is for a proportion. If I could spell, that would be great. Z sub alpha over 2 times the square root of p hat times q hat, all divided by what? N. It's not a hard formula to remember anyway. Okay. So, alright, so let's take a look at this. I'm not going to do a confidence interval yet. I know I got to that slide, but before we start actually forming the confidence intervals, we have to use the margin of error to find the confidence intervals. We also have to use the point estimate p hat. So how do we actually get those values from the problem before we get into constructing the confidence interval? Alright, so here's the problem we're going to look at from a 3M privacy filters poll in which respondents were asked to identify their favorite seat when they fly. N equals 806, X equals 492, whom chose the window seat. Use a 99% confidence interval. So we're not going to figure out the confidence interval. Use a 99% confidence level, sorry. We're not going to figure out the confidence interval yet. We'll come back to it in just a second. Let's first figure out p hat. And so it's a proportion. It's going to be the part that chose the window seat over the total. So what's the part that chose the window seat? 492 over 806. Alright, and we'll just round that to 3 decimal places whenever we find it. So we'll bring up a calculator. So 492 divided by 806. And I'm going to round that to 3 decimal places, so 0.610. All right, now the margin of error, we said that was critical value, critical z value, times the square root of p hat times q hat over n. Now I would use, when I find p hat and q hat, I would use this fraction here, or keep the decimal out to about 10 places. Because when you start multiplying decimals and taking the square root of decimals, that causes a lot of margin of error itself. So keep it as exact as possible. Okay, so my critical z-score, let me just write down the formula real quick. My critical z-score for a 99% confidence level, if you don't remember, look back at the table, or you can scroll back in your notes, or look back in your notes when we were talking about these common confidence levels and the critical value. For 99%, we use 2.575. Okay. That's going to be 2.575 times the square root of. Now I would actually use this fraction, or like I said, take it out to about 10 places, or just punch it in the calculator. 492 over 806. All right, and then that's p hat, so q hat, you say 1 minus p hat. So really all you have to do is say 806 minus 492. Right, that will give you your numerator for q hat. Well, 806 minus 492. So that's going to be 314. Is that right? So 314 over 806 all over n. Okay, so you might want to use some type of calculator that has parentheses. What I'm going to do first is I'm going to figure out this numerator. So I'm going to say parentheses 492 divided by 806, close parentheses. Then I'm going to say times, open parentheses. You see it's doing, uh-oh, I just pushed 80. So I'm glad it's showing me. Look at that. So make sure you, if you are typing this in your calculator, you're very careful. So 492 divided by 806 times 314 divided by 806. So you can see up here what's going on. All right. So then we want to say what? Divided by, what's n? And I'll put n down here, but what was our n? 806. Here, that's 806. Divided by 806. Okay. Now, what do we have to do? Once we find all that, take the square root of it. Then, say that times 2.575. All right, so I'm going to round that to 3 places. So, and when I say I'm going to round it actually to 3 significant digits. So that's 0.0442. 0.0442. Since I had a 0 in front, I decided 3 significant digits rather than just 3 places. Okay, so that's my margin of error. So I have a p hat, that's my point estimate that came from the sample, and I have my margin of error. Now, we're going to go and look at the actual confidence interval. Okay, with the confidence interval, we have p hat, n, the numbers, the sample of items, number of the sample items. Capital E is the margin of error. Z sub alpha over 2 is the critical value. Alright, so for a confidence interval, the sample is a simple random sample. The conditions for the binomial distribution are satisfied, and there are at least 5 successes and 5 failures. Alright, here's how we form the confidence interval. P hat minus E and P hat plus E are the outer numbers. The inner number is just P. This P is the population proportion. We don't know what that is, but we can figure out this interval, P hat minus E, P hat plus E. Alright, so let's go back to our problem we were looking at, and let's construct a confidence interval. So we want to say P hat minus E is less than P is less than P hat plus E. Now the best way to construct this is to carry these out, 4, 5, 6 decimals, but since I didn't, that'll be okay, because we eventually want to round it to 3 significant digits. So P hat is 0.610 minus the margin of error, 0.0442. That's less than P. It's less than 0.610 plus 0.0442. Alright, so calculator work. Alright, so if I rounded that to 3 significant digits, or 3 digits, that's going to be 0.566. So 0.566 is less than P is less than, I need to figure this one out, the upper limit, 0.610 plus 0.0442. So round that to 3 digits, 0.654. 0.654. Alright, so this here is my confidence interval. Alright, now to construct confidence intervals using other parameters like mean or standard deviation, we're going to do the same type of stuff. We're going to have that parameter, somehow we figure it out or it's given to us. We're going to have a formula that's not going to be the same formula, but we're going to have a formula to find the margin of error, E equals something, and then we're going to construct our confidence interval the same way. Alright, the confidence level can change, the way that you get the margin of error can change, but we're basically going to be doing the same thing for all the sections in Chapter 7. It's just a little different here and there. Okay? Sometimes my little different may differ from what you consider to be a little different, but hopefully not too bad. All right, so this is what we're finding. P hat plus or minus E. If you wanted to write that as an interval, kind of like you would, you know, if you were in an algebra class, how you usually write intervals, you could write this interval here just like this if you wanted to, 0.566 to 0.654. Okay? It means the same thing. All right. Round the confidence interval limits to 3 significant digits. If you can help not rounding before you get your final answer, you know, if you're using a really good calculator and you're pretty comfortable with it, then there are ways for you know to store answers and to scroll back up and look at answers and things like that. So I would suggest not rounding until the very end. But if you have to, then you have to. Then, you know, round 4 or 5 digits or whatever, do your calculations, and then round at the end. But just know if you're off by a thousandth of what you should get, it was probably because you rounded too soon. All right. So now your book or these slides are going to go through step by step of what we just did. All right, and here's an example. Let's just read through the example instead of working it since we just worked one. So here is a, this talks about the chapter problem. This is going back to Twitter. 85% of adults know what Twitter is what they're saying. From this sample of 1,007 people. I would be willing to bet that 85% of all college students probably have a Twitter account now. I mean, it's getting a little more popular. All right, so N is 1,007, and P hat is 0.70. Okay, so the first thing that we would want to do is find the margin of error that corresponds to a 95% confidence level. That's if we want to be 95% confident. And so we have to use the critical z-score for 95%. Anybody remember what that was? 1.96, right? If you don't remember that, you can go back to your z-score chart, and it's at the bottom in one of those little tables. And then here's the other things we're going to do with this problem. It says, can we safely conclude that more than 75% of adults know what Twitter is? I'm wondering if, so it's a good thing you have one of the smartest statistics teachers in the world, or at least in Western Mississippi. I'm probably top 10. P hat is not 0.70, it's 0.85, so this slide is wrong. Thank you, Pearson. So that needs to be 0.85. Okay. Top 10 in Western Mississippi, guaranteed. All right. So to find the margin of error, you have the critical z-score here. We said it was 1.96. P hat is 0.85, and if P hat is 0.85, then Q hat is 0.15 because it's 1 minus 0.85. Over N, the sample size was 1,007. So you see they carried their margin of error out to many places, 7 places. That's a good idea so that you don't have any rounding errors in the final answer. All right. So 0.85, that was your proportion, right? It's 0.85 minus your margin of error, and 0.85 plus your margin of error. Once you do that, then round to 3 places, and you got your confidence interval. All right. Based on the confidence interval obtained in Part B, does it appear that more than 75% of adults know what Twitter is? Here are the limits here. So that's 87.2% and 82.8%. So if we want to know, does it appear that more than 75% know what Twitter is? Yes, it does. I mean, it appears to be, or you know, that you could make that conclusion. And then it says here's one statement that summarizes the results. 85% of U.S. adults know what Twitter is. That percentage is based on a Pew Research Center poll of 1,007 randomly selected adults. In theory, in 95% of such polls, the percentage should differ by no more than 2.2 percentage points in either direction from the percentage that would be found by interviewing all adults in the United States. So that's where the whole 87 point whatever percent to 82 or 83 point whatever percent came from. All right, another caution. Cautions are good. Never follow the common misconception that poll results are unreliable if the sample size is a small percentage of the population size. The population size is usually not a factor in determining the reliability of a poll. All right, so how do we know how many people that we need to poll, though? If 1,007 worked for their study, then how many sample items do we need to obtain so that we can make an estimate about some population? Well, we have a formula for that. Okay. To find the sample size n, then you know, you could solve for n here. Well, it's already been done for you. And we know that if you do know p hat, so you have some point estimate of a sample, then you say z sub alpha over 2 squared times p hat times q hat divided by the margin of error squared. All right, so z sub alpha over 2 squared times p hat times q hat all over the margin of error squared. If you do not know the point estimate, that's the value from the sample size, all right, then we say the critical value squared times 0.25 all over the margin of error squared. If the computed sample size n is not a whole number, round the value of n up to the nearest larger whole number. Okay, so as a sample size, you can't have 1,006.8 participants. All right, you'd have to have 1,007. But it says to round up. Okay. So let's look at this example. Many companies are interested in knowing the percentage of adults who buy clothing online. How many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? So that means a margin of error of 3 percentage points. All right, so what sample size do we need? All right, so first we're going to use a recent result from the Census Bureau. 66% of adults buy clothing online. All right, so that is our point estimate, or p hat. So p hat is 0.66. All right. Our margin of error, it said by no more than 3 percentage points. So we don't have to worry about actually calculating that. It says 3 percentage points would be 0.03. Okay. Now, if we know what Q hat is, or I'm sorry, if we know what P hat is, we can find Q hat. If we know what confidence level is in the problem, then we can figure out the critical z-score. So 95% confident. That's a confidence level for 95%, which we figured out earlier. So z sub alpha over 2. It's 1.96. That's for 95% confidence level. Okay. So let's use our formula. Well, we need to write down what Q hat is. 1 minus 0.66 is 0.34. So that's Q hat. So N equals z sub alpha over 2 squared times P hat times Q hat over the margin of error squared. So that's what we're going to do. Alright, so if we do that, here's our margin of error, 1.96. Here's our Q hat, or our P hat, and our Q hat, 0.66 and 0.34. We were given the margin of error. We didn't have to figure it out. We were given it was 0.03. And so if you punch all that in your calculator, you get 957.839. All right, and if we round that to the nearest whole number, or we round it up to the nearest whole number, that is 958. So that's your sample size, 958. All right. Now, if we don't have a point estimate to go with, I believe that was part B, assume we have no prior information. So we use the formula with 0.25 here as P hat times Q hat. Of course, this is a really rough estimate. If you're just saying 0.25 for P hat times Q hat, that's got to be a really rough estimate. Plug all those same values in, square, divide, and you get 1,068. So if you have no sample to go on, the estimate is 1,068. That's how many data items you would need. If you have a P hat of 66%, then we found out that it's actually smaller. Alright, you can figure out the point estimate if you have just the confidence interval. To find the point estimate, you say the upper confidence limit plus the lower confidence limit divided by 2. That will give you your P hat, or your point estimate. That's if you just have the confidence level. All right. You can find the margin of error if you just have the confidence interval. You say the upper confidence limit minus the lower confidence limit and divide by 2, and that'll give you the margin of error. So if all you had was the confidence interval, this is how you could get the margin of error and the point estimate, p-hat. Okay. Now, depending on what statistics or what parameter we look at, I told you that your formulas are going to be a little different. Okay. If we're talking about a mean, population mean, okay, we should know the sample mean, or we need to know the sample mean. That's our best point estimate of mu. Okay, so we'll be able to figure out the sample mean really easily, or not too complex calculations, or we'll just be given the sample mean. Okay. To do this, it says we need to make sure that the population is normally distributed or the sample size is greater than 30. That's just binomial distribution type stuff. The margin of error is found a little differently. If we don't know what the standard deviation is, the population standard deviation. Alright, so to find the margin of error for confidence intervals that involve the mean, we need to say that the margin of error is equal to, I don't see z sub alpha over 2, I see something called t sub alpha over 2. This is a critical t-score. So if we do not know the population standard deviation, we're going to have to use a different table to find a critical t value. All right, because if we don't know the standard deviation, the population standard deviation, it's a t distribution. Now, what is s? Lowercase s. That is sample standard deviation. Okay. All right, so critical t, again, is going to come from the t distribution chart. This is sample standard deviation, and then n is the number of data items. So the critical t chart is the chart that's right after the critical z chart. Now, to use it, we have something called degrees of freedom. Degrees of freedom, you take the number of data items and you subtract 1. Alright, so that means if you have 30 data items, you say 30 minus 1, and we'll use the value for 29. So that's the way degrees of freedom work. N minus 1. Okay? So that's where we'll pick up with the next class.